Good morning. Welcome you all to our course Radiation Oncology Physics, and today we are going to start the fourth week of our course, where we will discuss the various type of classical radiation oncology treatment planning and all the physics related to our patient treatment in our radiation oncology, and we will discuss the classical form, or you may call it as conventional form of radiation oncology. And this is the fourth week and the lecture number is 16. Today we will discuss the central axis depth dose parameters and isodose charts. Now, learning objectives of our today's class is central axis depth dose parameters, and they are percentage depth dose parameter, percentage depth dose, they are tissue air ratio TAR, they are backscatter factor BSF, and we are going to discuss the tissue maximum ratio TMR. So, why these all kind of parameter are defined to for the use of treatment planning or treatment dose calculations or dose distribution of patients, it will be discussed in our following slides. Now, ideally in the method of dose calculations, or if we want to predict, if we want to get the dose distribution of the patients, how these patients receive the dose, or we should have able to measure the radiation dose in the patients. Directly we should have some facility to measure the radiation dose in the patients, but these are type of, there are various kinds of measurements are also available where we can directly measure the radiation dose to the patients, but there are many limitations of accessibility and suitable detector systems, and there are so many problems. This is not possible most of the time in our radiation oncology department dose calculation, or to predict the dose distribution, or to calculate the dose of which is actually received by the patients during their treatment. So, what we do, we actually measure the dose distribution and we produce the dose distribution data in some tissue equivalent material. They are not patients, tissue equivalent materials, and which gives the full scattering environment. Means we should have such volume that the whole full scattering environment is provided to measure the dose distribution data in the tissue equivalent materials, not in the patients. So, these basic data is used in dose calculation systems. It may be treatment plan, computerized treatment planning system, or it may be manual calculation system. Now, prediction of dose distribution is simulated using high-end mathematics. Using these basic data, we use various kinds of models, various kinds of algorithms, and various types of calculations computers. They are actually predict the dose distribution using these measured data which we have produced in during our measurement process. They are these data are used for to simulate or to predict the dose distribution in the treatment of cancer patients. These are some terminology you might have heard about this or may not, and this is one kind of thing which we regularly use in radiation oncology. They are known as phantoms. Now, what is phantoms? This basic dose distribution data is measured in tissue equivalent materials of large volume. They are actually known as phantom. And in our radiation oncology, we normally use water phantom is commonly used, and because the water have the very unique features that water is closely approximate the muscles and other soft tissues of human body. So, the radiation absorptions and scattering of the radiation scattering are almost same in water as in the muscles and other soft tissue of human body. And the second one, their water is features, the advantageous feature is this is the water is universally available, and the radiation properties are reproducible from time to time. If we measure the same amount of radiation beam or radiation field, the water will not affect or water will reproduce the same reading for each time. So, this is known as reproducibility of the measurement, and water is a very reproducible phantom material which reproduce the radiation properties similar fashion for every time. Now, there are some problems or limitations of water phantom, because we need to immerse radiation detectors. These radiation detectors, you know that during our dose measurement we have discussed that we applied the anode and the cathode a very high potential up to 300 volt. So, there is a waterproofing of the detector is must for using the water phantom. So, we actually encased the detectors with proper waterproofing. So, we can waterproof our detector, or we can change our water to the similar kind of solid materials. They are known as solid water phantom. So, this is all about phantoms. We use these, we generate or we measure the basic dose distribution in tissue equivalent and in large volume of phantoms. They are known as phantoms. So, you must understand that why water is used and what are the problems of using water as a phantom materials. Here is two kind of phantoms in this slide. First one is, this one is a water phantom, where you can see this is filled with the water, this is water filled with this is type of aquarium type of things, and we placed a detector systems, and this detector system, the dose is measured by this outer unit, and this is the water phantom, and this is the solid water phantom. They are available in form of sheets, or they sometimes available in form of special design. They are actually solid water phantoms, where the waterproofing problem is not there. Now, depth dose distribution or CADD data. Central axis depth dose. The beam incident on a patient or phantom, the absorbed dose varies. These absorbed dose varies the following parameters. First is beam energy. If beam energy is higher, the absorbed dose is different, or it is increased for any particular point. Suppose this is the point where if we increase the dose beam energy, the dose will be higher in this point. Now, if we increase the depth of the measurement, this is the absorbed dose also decrease, means the lower depth the absorbed dose is higher. Now, if we increase the field size, the absorbed dose will increase. If we increase the source to surface distance, then also source to surface distance we have discussed. This is the source to surface of the patient or surface of the phantom distance, and this is also a important parameter which defines the absorbed dose variations and the beam type of beam collimation systems. Now, the calculation of radiation dose is, we need to consider all the above parameters mentioned, that is beam energy, that is depth, that is source to surface distance, source to and beam collimation systems, and these are how these parameters are affecting the radiation absorbed dose. We need to establish a relation. So, first and essential step in dose calculation system is that we need to establish the depth dose variation along the central axis. These are actually beam divergence, and this is actually central axis. So, this is the essential and first step to calculate or to model the dose distribution or to establish a depth dose variation along this central axis, and these parameters are known as central axis depth dose parameters, and today we are going to discuss all these parameters one by one. Now, these are the central axis depth dose parameter. First one is percentage depth dose PDD, the tissue air ratio TAR, the backscatter factor BSF, and tissue maximum ratio TMR. Now percentage depth dose. Percentage depth dose is the normalizing of the dose of any point with a reference point, dose to a reference point. So in this diagram you can see that we have a source, we have a collimating system which defines the radiation beam, and we have a phantom here, and this is beam divergence, diverging side, and this is central axis. Now this is the percentage depth dose is the normalizing the dose of any point. This is the point, this is the point at any depth, and with a dose to the reference depth if we consider a reference point. So we need to normalize the dose at any depth to the dose at any reference point. So this is actually the quotient of dose at given depth to the dose at reference depth, and this is expressed in the percentage. Dose at given depth to the dose at reference depth. This is a quotient expressed in percentage. So this is the percentage depth dose. Here this is the source to surface distance SSD, and this is one more parameter, this is SDD. This is actually defines the collimation system, source to diaphragm distance. Now the PDD is DD here, this is the DD, the dose at D depth divided by dose at reference depth and multiplied by 100. So this is expressed in percentage. So this is the percentage depth dose, and if this D difference is replaced by the D reference is replaced by D maximum, then we call this is a percentage depth dose at D maximum. So we normally use the depth of dose maximum as a reference depth. One may use the reference depth for maybe 5 centimeters, 10 centimeter, or whatever they want. But this is actually normalizing the dose and of any depth to the dose at reference depth and expressed in percentage. So this is the PDD for different kind of photon beams available in for treatment of cancer patients. The first one is 3 millimeter. First one is 3 millimeter HBL of copper. This is from kilo voltage unit, and this one is cobalt 60 unit. This is 4 MB unit, and this is for 10 mega voltage, and this is for 25 mega voltage. Now you observe that if we increase the energy of the photon beam from kilo voltage to mega voltage, from up to 25 mega voltage, that it started from the zero depth, the dose is at the zero depth the dose is very less, and it is increasing and it reaches up to the maximum, and then it again decrease with the depth in the water. And this is known as the depth of dose maximum. This is known as depth of dose maximum, and this depth of dose maximum increases with the increasing energy. You can see this is the depth of dose maximum of cobalt. This is approximately 0.5 centimeter, and this is the depth of dose maximum of 4 MB, and this is the depth of dose maximum of 10 MB. This is the depth of dose maximum of 25 MV photon beam. So there is a initial percentage depth dose is less, then it again increases with depth, and after getting the maximum dose maximum, it's again decreases with the depth in the water. Now high energy photon beams, we have observed that there is a initial build up region, and the point of maximum dose lies deeper into the tissue. So we will get a clinical advantage while using the high energy photon beam. They are known as skin sparing effect, means we can treat the deep seated tumors without giving dose to the higher dose to the skin. But if you see the low energy or kb ranges, they started from 100%, means skin will receive the 100% dose, almost maximum dose, and while treating the deep seated tumor. So this is the clinical advantage of using high energy photon beam, and this is known as skin sparing effect. Now physics behind this initial build up is we will discuss that the high energy photon beams enters the patient surface. The high speed electrons ejected from the surface and subsequent layers, and these electrons deposit their energy away from the origin, and the electron fluence means increases with the depth, and as well as absorbed dose increases with the depth. However, the photon fluence is continuously decreased with the depth because of attenuation, we have discussed during our interaction classes, and the net effect is that net effect of reduction of photon beam fluence and increase of electron beam fluence will, after certain depth, the depth dose is eventually decreased with the depth. So this is the physics behind the initial build up. Now PDD's dependence on the affecting factors. The PDD increases with the increase of beam energy. If we increase the beam energy, PDD will increase. Now, and PDD decreases with the increase of the depth, and PDD increases with the increase of the SSD, and PDD increases with the increase of field size. Therefore, PDD is the function of energy, depth, field size, and source to surface distance. So all these four parameters are affecting the percentage depth dose along the central axis. Now we know that PDD is the function of energy, depth, field size, and SSD, but this PDD is mostly applicable only for fixed SSD treatment setups, where our source to patient surface distance is fixed. We can use percentage depth dose, but there are nowadays, or there are very possibilities that we are going for such type of fixed SSD setup, because in current days we are using multiple beams for treatment. So for varying SSD, if our SSD changes from each field treatment setup, we need to calculate the PDD for different SSD. But this calculation needs, there are methods by which we can convert our PDD for different SSD, but they are very laborious, and this is not possible for all time. So SSD dependence limits the PDD in use of multiple or rotational therapy. We will not able to use the percentage depth dose as central axis depth dose parameters. So we need to formulate SSD independent parameter, the central axis depth dose parameter, which will suitable for multiple or rotational beam therapy. Now the solution is tissue AR ratio, or TAR. It is defined because of previous limitations. Here we have similar setup where this is the source, same source, we have the same kind of beam divergence, means the field size is same, and we have the same distance, the point of measurement is same, point of measurement distance is same, and this is known as SAD. This is a new terminology. This is source to axis distance, and this is distance. This distance is fixed for each machines, and this SAD source to axis distance may be 80 centimeter or maybe 100 centimeter as per the equipments, or as per our requirement. So the point of measurement distance is same with the same setup. Now you must observe, you must notice that there is a difference in measurement. Here we have apply a phantom, and here it is free space, means there is no phantom. We have to measure the dose at air. Now the ratio of dose at any point in phantom, this is any depth in phantom with a dose at the same point in free space. This is the ratio of dose of any point in phantom with a dose to the same point in the free space. So TAR, so here as we have keep the measurement distance same, so we can this parameter is independent of SSD or independent of distance. So TAR is TD at D depth and DFS at free space at the same point. Again the dependence TAR, dependence affecting parameters, TAR increases with the beam energy as similar to the PDD, and TAR decreases with the increase of the depth, and TAR increases with the increasing of the field size. Therefore TAR is a function of E energy, the depth and the field size. We have eliminate the dependence of distance from this parameter. Now backscatter factor, this is the TAR at the depth of dose maximum. This is depth of dose maximum, I have already discussed, and BSF is Dmax and DFS. You can see this is the dose at depth of dose maximum, and this is the dose at the same point, means the distance we maintain this distance SAD, and this is the ratio of Dmax divided by DFS. So this is the backscatter factor. Now the limitations of the TAR, because beam energy, if we use the beam energy higher than cobalt 60, there is a compromised in the measurement at free space, because we need to have a very thick chamber build-up cap as beam energy increases. This is we have discussed during the electronic equilibrium during our measurement class, and you may correlate with that phenomenon with these limitations of the TAR, because in free space the measurement is very much compromised and very much questionable beyond the energy. Beam energy is higher than the cobalt 60 radiation. So the second problem is the materials of build-up cap is different from the phantom materials. For accurate dose calculation, there is a need to have a more robust parameters which eliminates the above limitations, means the compromise measurements of free space and the distance dependence of the source to surface distance. Now here again this is we have a same kind of measurement system, same field size, divergence, same kind of divergence, and source, this is source, and measurement distance is SAD, but in previous definition of TAR, here we use the phantom. Here the measurement point is same, distance is same, but depth is different. Here depth is D and here depth is D maximum. So ratio of the dose at any depth in phantom with the dose at the same point in the phantom at reference dose, and TMR is DD divided by D max, or you can call it as D reference. You can use the reference point as depth of dose maximum, or you may use the any kind of any point as per your requirement. It may be 5 centimeter depth, it may be 10 centimeter depth. So TMR, the tissue maximum ratio, is the ratio of dose of any depth in phantom with the dose at same point in the phantom at reference depth. So TMR is DD, D capital D is the dose, absorbed dose at D depth, and D max or D reference. So this is all from our today's class, and in this class we have discussed the various central axis depth dose parameters and percentage depth dose, like tissue area ratio, backscatter factor, and tissue maximum ratio. Thank you.